My name is Angelica Logan,
My name is Chelsea Norwood.
And I'm Lyric Baldridge.
and we are doing ultrasound imaging. Okay, so sound waves. They are longitudinal waves that travel through a medium, for example, air or water, but they are incapable of traveling through a vacuum. And this makes them an example of a mechanical wave. So the region of increased pressure on a sound wave is called a compression or crest. And then where there is decreased pressure on a sound wave, it is called a rarefactant or a trough. And then the amplitude of a wave, it tells how forceful or loud that wave is. And the amplitude is measured in units called decibels, and it is measured on a logarithmic scale. Okay, so speed of sound, waves travel. I'm so sorry, y'all. Give me 1 second because my parents are really loud right now. Do y'all mind if we start over?
Yeah, that's fine.
Okay.
I can't even hear them.
I can't, and it's bothering me. So give me 1 second.
Okay.
Okay, I'm back. Sorry about that. Okay, so y'all ready to start?
Yeah.
Okay.
Yeah.
All right. My name is Angelica Wogu,
I'm Chelsea Norwood.
And I'm Lyric Baldridge.
and we are doing ultrasound imaging. So, sound waves. They are longitudinal waves that travel through a medium like air or water, but they are incapable of traveling through a vacuum, and this makes them an example of a mechanical wave. And the region of increased pressure on the sound wave is called a compression or a crest. And then where there's decreased pressure on the sound wave, it is called a refractant or a trough. And then the amplitude of a wave, it tells you how forceful or how loud that wave is. And it is measured in decibels and on a logarithmic scale. So the speed of sound, waves spread with a certain speed, and the general equation for a speed of a mechanical wave is the square root of the elastic property over inertial property. And temperature and pressure play a role in affecting elastic and inertial properties. And for elasticity, that is the rigidity or the stretchiness of a material, and then inertial defines the mass or the density. Speed is proportional to the material's rigidity. So as that increases, the speed will also increase. And then for elasticity, as that increases, speed will decrease. Speed is also inversely proportional to mass or inertia. And as density increases, speed will decrease. And speed travels through different mediums at different speeds, slowest in air and fastest in solids. And then this is the equation for the speed of sound in ideal gas. And it depends on the type of medium, such as air, liquid, or solid, and then the temperature of that medium. And that equation is the square root of the ratio of specific heats multiplied by the gas constant multiplied by the absolute temperature. And then the speed of sound can also change with atmospheric conditions, such as altitude, temperature, and humidity.
Okay, so there's differences between sound waves, which can be measured. There's audible, infrasonic, and ultrasonic. When within the range of human ear sensitivity, the frequencies are also measured in hertz. So for human ear frequency sensitivity, it's going to be 20 to 20,000 hertz, and for sonic, for wave frequencies that are below the audible range are usually less than 20 hertz, and then anything higher than the audible range is usually greater than 20,000 hertz. And so this diagram just kind of shows the different audible ranges that different animals can hear. So obviously, so as we can see, like elephant on the scale is usually less than 20 hertz, and then you have like dolphins that are usually greater than 20,000.
Now that we've had an introduction to sound waves and had a better understanding, let's talk about the ultrasound imaging. Ultrasound is an imaging method that uses high frequency sound waves to produce images from within the body and outside the body. There are different types of ultrasound imaging, such as 2D, which is a slice of a 3D object, 3D, which is several 2D images taken by multiple probes brought together to create the 3D image. And then you also have Doppler imaging, which measures sound waves reflected by moving objects such as red blood cells. Common uses of ultrasound imaging are to view the uterus and ovaries during pregnancy and to monitor the developing baby's health, evaluate blood flow. And with this one, you would definitely use the Doppler imaging, since you're talking about the flow of blood and that requires movement. You also can assess joint inflammation, check thyroid glands, examine breast lumps. And to do all of this, we have to have some essential ingredients. So for ultrasound imaging, you need an ultrasonographer, an ultrasound machine, mineral-based jelly, and an ultrasound probe or a transducer, which can be placed both outside and inside of the patient's body.
All right, so in order to, I guess, understand the safety principles used for like, minimizing radiation exposure, we need to understand how waves play a role in ultrasound imaging. So waves, they generally transfer energy through oscillations, which is moving at a distance about the equilibrium position, as we see in this diagram as the waves go up and down. The two terms that we use to describe a wave are cycle and period. So a cycle is usually on the y-axis and is the length of one positive and negative deflection. And then a period is usually on the x-axis and is the length of time to complete one cycle. Frequency is the number of cycles per second in hertz. And a wave with lower frequency has a lower energy, lower wavelengths, and the crests are usually further apart. And vice versa for higher frequency, where the waves are going to be usually closer together, which has more cycles per second. Amplitude, the height of the wave, which can be used to measure how much energy the wave carries, and then wavelength, which is the distance between two similar points on a wave. And not to be confused with period, which deals with time. How sound waves are generated. So we have piezoelectric crystals, which are placed inside of the probe. The electrical charge is applied to the crystals, which causes mechanical pressure. And then when the mechanical pressure is applied, the crystals, they start to vibrate, creating this ultrasonic sound wave. And then they're directed into the body using a gel, which, as we stated before, it makes it easier for these waves to travel through this liquid material. So the pulsated waves allow the crystals to send out those sound waves, and then we're listening for them for the returning sound waves as well.
So now that we've been able to learn about ultrasound imaging and how sound waves are used in this type of imaging, we want to make it a point that ultrasound imaging is a great method to be used. With this method, you can capture images of soft tissue, which cannot be done with x-rays. Patients aren't exposed to radiation during the process like they would be if they were to use CT scanning or x-rays. And you can also take it a step further with the 3D imaging, which we have an example of on the right. It allows physicians to get a better view of what they're looking for, such as detecting cancerous and benign cancerous and benign tumors, fetus development, and blood flow in various organs or fetus. And another interesting thing about ultrasound imaging is the ability to combine the two types. So there's anatomical and functional. With anatomical, this uses the images of internal organs, while functional combines movement and velocity of the tissues and bloods. And together, when these two are combined, it creates these information maps that allows physicians to get a better picture of what they're looking into. And overall, ultrasound imaging is a great method, but there is research being done on how to improve these images and make them of higher quality, greater than they currently are. And please feel free to add any questions below or any comments, and we'll be happy to answer them as a group for you. Thank you and have a great day.